Hi, everyone. Welcome to this afternoon session. I hope you all had a great lunch. My name is Valerie Fennick. You'll be seeing a lot of me around this week, I think, from Oracle. I would like to take this time to introduce our first presenters in this session. We're going to have Apostle Vassilev from NIST and Barry Fussel from Cisco. Thank you very much. Oh, and real quick, as a reminder, I will make you use the microphone for questions because these sessions are all being recorded, and when you listen back, it's really awful when you can't hear the questions because the answers don't make any sense. So please do use the microphone. I know you have to walk over, but I do appreciate it. Thank you very much. Welcome, Apostle.
Thank you. Thank you, Valerie, for the introduction. This is going to be a three-part talk. The first part is going to be by me, essentially setting the context up, and then I'm going to turn it over to Barry for the technical, substantive part of the talk, and then we're going to finish it off with a demo, which is actually a very cool video. I know it's right after lunch, and I promise you that we have something cool to see in the end, if that's going to spike up your interest a little bit. But that's the plan. Okay, so let's get to it. Let's start with traditional conformance testing and why we're doing what we think we need to be doing. So the traditional conformance testing is shown on this diagram, and it basically goes linearly from left to right, where the vendor designs and produces modules. They define the boundary of what they think the module should be, figure out what services go into the module, the approved mode of operation, write the security policy, and so on. Then a laboratory picks it up and does some testing, algorithm testing, as well as documentation reviews, source code reviews to ensure that the module is implemented correctly, operational and physical testing, all these things. Once the testing is complete, the laboratory produces a report which then gets submitted to the CMVP for review and validation. If all goes well, then NIST issues a certificate. And based on that, users in the federal space can procure modules and use them in their infrastructure. And so if you look at this slide, it gives you a feeling of a very well-designed, ordered process, goes from left to right, and it's kind of reminiscent of the so-called waterfall model of designing technology from back the, say, late 80s to mid 90s, which was the de facto process that many of the technology organizations used to develop technology. And I think that waterfall model was appropriate for the pace of technology back then. If you put a time dimension on this slide and project yourself back to, say, the early 90s, you will see that the pace of technology there was very, very different. And on top of that, if you think about the cybersecurity challenges of the early 90s, you could safely say, well, this is the sort of the adolescent years of what cybersecurity looks today, right? And so how does it really look today? And so a good place to sort of examine this question is the Verizon breach investigation report. So this is sort of a 30,000 feet view of what's happening in cybersecurity today, and it's mostly handling or considering the problem in the context of the industry. It doesn't cover really the government space, but you know, you could easily, if you have followed the press from the last several years, you'll see that there's a lot of parallels to be drawn. And so, what this report says, it's an annual report, by the way, and it's in 9th year of edition. So, if you're looking for an exciting read about cybersecurity, that's a good place to go. And so, what it shows is really kind of unusual, startling information it gives us. So one is that most attacks that are exploited today actually start with vulnerabilities that have been known and patched for a very long time. That's the conclusion of the report this year. This was the conclusion last year, and the same conclusion many years ago. So that's a huge problem that exists there. And certainly we have a huge number of CVEs, or common vulnerabilities and exposures, and we at NIST maintain an NVD service that gives you a whole list of that. But even then, if you say, well, the problem is too big, so that gives a huge door open to attackers. But even then, it's the top 10 vulnerabilities that are most exploitable, and so that's a serious issue. How do you deal with patching? And the problem here is that, well, 58% of businesses don't have mature patch management process. So basically, people are struggling with the notion of patching. And so last year, I gave a talk here at this conference that talked about, first of all, why do we have patching in the first place? And the message there was that the reasons for that are not just technical, but there are economic principles or reasons which sort of led us to get into this mode of having to patch all the time. And I'll touch on this a little later in my talk. It also tells us that attackers are getting really much better than they used to be. And in 93% of the cases that industry has reported as breaches, it took just minutes to abuse the systems or to gain to get the assets these attackers are looking for. So you're going to be fooling yourself if you think that, oh, we have these vulnerabilities, but I have some intrusion detection system in-house that would allow me to catch them while this is happening. This is actually not supported by the record. It sounds like attackers are much more efficient in detecting and abusing systems. And of course, most breaches are about money. So anything that can be monetized is a target. And of course, cyber espionage is something that has propped up quite a bit recently. So if you have some sort of a business secret or know-how or some intellectual property that can be monetized, watch out for it. And certainly, it's a big issue for us. Again, I said that this does not cover government systems, but just think about what happened last year or so with OPM and other things that suggest what the issues are. And to be fair, not all of these CVEs are cryptography related. However, if you think about how modules work, they don't work in a vacuum. They work in an operational environment. So anytime you patch, you are going to affect either the module itself or the environment in which the module works. Therefore, you'll be touching upon the validation in some way or form. Okay. So, okay, we said, all right, these are the challenges. What can we do about it? And if you look at the sort of the validation program as it exists, one of the issues that constantly comes back to us, the message from the industry is that, well, it's a long validation cycle, well beyond the typical product development cycle today. I mean, we talked about mid-90s. Maybe the product cycle then was long enough to sustain the existing validation cycles, but the message from the industry is, it's not, it's too long. The other thing, and of course the upshot of that is that not only does it slow down the business of industry and their ability to sort of sell technology to the federal government, but on the flip side, agencies are unable to pick up latest technology in a timely fashion. We all have to wait for the validation cycle to complete so that it can be procured in federal systems. Another issue that is constantly reported to us is the shallow depth of testing. The software testing methodology is somewhat dated for today's challenges. I mentioned today the primary technology, the primary technique we use to validate the conformance of the modules to the standard is code reviews. And code reviews nowadays are not the most efficient way to identify problems. In particular, if you look at the sort of the industry measures as to of the efficacy of this approach, you realize that people report that the bug discovery rate of code reviews are on the order of 50%. So basically, it's labor intensive and it's not very effective. So it's not to say, the message that I'm giving here is not to say that code reviews have no place. In fact, David made a good point earlier this morning in his keynote, saying that, yeah, you have to do some sort of review if you want to attest something to the faithfulness of your module to see how well it adheres to its official mission. But it is important to know whether or not the techniques you're using are the best techniques for the job that they have to do. And so that's one area of concern. The other thing is that the validation program, the way it is structured today, tends to be costly and rigid. For example, it's difficult to obtain actually compliance assurance on platforms of actual use. I mentioned the patching issue a few minutes ago. So as soon as you start patching your environment, it is very likely that the federal agencies, when they procure modules, they're going to use them in different environments than those that were tested on, and it's a real issue, and because it is lengthy, costly, and rigid, it limits the ability of the industry to actually validate more products so that they can be available to federal users when they need them. And in particular, it prevents the industry from fixing critical problems, in particular those that are CVE related in time frame that is required. Remember, we talked about that patching now is important for everyone. Without patching, you're dead in water. And so you have to do it efficiently. But then the dilemma for the industry becomes, do I keep my FIPS validation, or do I fix my my CVEs, right? And that's a false choice, I think, for nowadays. We have to be able to do both. So we tried very hard to sort of solve all these issues in the box of the existing program. And I know the last couple of days the laboratories met with the CMVP, and a lot of improvements have been made in terms of improving all the inefficiencies that were there in order to process the validations in the way the original program was structured. And that's all we have done. We have done all of these things, and still we're thinking that our validation cycles are too long to accommodate the challenges in terms of product development cycles and ability to patch and maintain validation status. The other issue that we find a real hard problem to solve is the problem of objectivity of validation results, right? By definition, a conformance testing program has to be objective. It is the same set of requirements, and if you have similar technology, you have to meet them the same way for everybody. And yet, when you have different companies, when you have different laboratories, and you have different validators, and they all rely on written test reports, which look and feel more or less like an English essay, right? And the complexity of these essays has gone to a level totally unprecedented compared to the origins of the program. You have so many different algorithms, protocols, different sort of complexity about science and implementation that when you put it on paper, it becomes dizzying to read all of that stuff. And so as we are struggling to improve our consistency in validating reports, as we are struggling to achieve this objectiveness of validations, this is a real problem, a elusive target to chase with the existing structure of the program. And that's an open problem we took to heart to our management. And they said, well, why don't you ask the industry for input of what technology looks like today, what are the best methodologies to test it, and what can we do to structure the program accordingly. And so we did that. And last year we announced our intent to start a working group with the industry. There was a couple of conferences. One of them was the previous edition of ICMC 15, where I announced our intent to start the group, and we actually initiated it with a founding face-to-face meeting at NIST. And that photo is not an actual photo from the meeting, but not far from it. I think everybody who attended there would agree that we had a couple of days of really spirited discussion and a lot of aha moments. But that's history now. And really the goals of this working group is to provide powerful economic incentive to the industry. On one hand, to reduce the length and cost of validations, and of course to hopefully enable just-in-time validations through verifiable test artifacts. Remember that when I mentioned my talk last year, I said the problem is not just technical. The problem is also economics, right? So when if you want to make changes to cybersecurity today in the industry, you have to sort of address every problem at their level in order to hope that you're going to get a good result out of it. So we can be talking security all day long, but if there is no economic backing to what we're saying, nothing's going to happen. And so, part of the reason of why we want to integrate, sort of work with the industry, is to understand their business constraints and come up with solutions that play well within their business models. And that's part of the incentive here or part of the goal here is to come up with the structure of the program that is conducive of them doing business and enables them to do many more and much quicker validations, because that serves them, serves the government as well, for the reasons that we already discussed. We also want to widen the agency's access to latest technologies, right? We don't want them to, again, face the false choice of do they maintain FISMA compliance or do they patch? We want them to be able to do that. And here is my feeble attempt to remind everybody of the Heartbleed problem that we had a couple of years ago. I hope most of you remember it. And just to think of it, you know, we have a symbol now that is gone in pop culture signifying or identifying a well-known computer code error, right? So think of the times that we live in. And of course, we would like to align our program better with other government test programs. One of the perhaps one of the maybe the number one questions that comes from our NIAP colleagues is, well, the environment for your algorithm testing don't match our environments for common criteria, right? So there's always this discrepancy, versions, patches, whatnot. And it's hard to reconcile the two. And again, if you can come up with ways to actually address this problem, it will go a long way. It will go a long way for the industry and for the government agencies as well. And so that's a goal of this working group. And so as we sort of set up the group and organized it, right now it is chaired by me, and I'm helped by Melanie Cook at NIST. And so the group is divided into 5 working areas, and each area has a lead for the corresponding area. The first area is algorithm test, and it's led by Barry, who's sitting next to me, and David. And then we'll have software and module testing automation. That's led by Microsoft, Tim Myers. The hardware module test automation is led by Intel with DJ Johnson and Greg Piper. And of course, we want to tackle the problem of validating modules in the cloud. Cloud is a very interesting area to the government. A lot of our services are moving into it. And that because of the constraints of the program of having a well-defined platform, which is elusive on the cloud, this is something that we need to address in the near future. And so we have set up a working area in that arena, and it's led by Amazon Web Services. And finally, it's the government coordination. That's basically the mechanism of feeding the results from, or the input from, the industry group back into the government agencies to NIAP, other programs that are interested in it. Essentially, think of it as the government coordination group is sort of a very loose project management unit for the whole working group to work. And as you can see, a lot of companies have joined into this effort. By far, the most membership is in the software module arena. I don't know if it is, the reason for this is because software is not handled very well by the current program, or because simply we have more software than hardware nowadays. I don't know, but it's an interesting observation. We are open to participation, and at this stage we're going to take a stage approach to developing the reorganization of the program, but at this stage we are looking for participation by technology companies who are producing cryptographic technology. And later we'll find ways to engage the laboratories and see how we can restructure the program. But essentially that's what the structure of the group looks like at the moment. And where are we? Well, we're still in the process of scoping the work. We are finalizing the charter documents for each work area, which will identify the scope of testing automation that each work area is going to pursue. And to do that, we are going through a process of analyzing the derived test requirements, how they apply to the classes of technology that are in the corresponding working areas, and perhaps identifying ways to automate that. And so I'm very happy today to report to you that we have reached our first milestone. We have developed actually an automated cryptography validation protocol, an automated algorithm validation system. And to show you all that, we also have the automation demo and video that we're going to show at the very end. But with that, let me turn it to Barry for the substantive part of the work, of the talk now.
Thank you, Fussel.
Yeah.
As you heard, my name is Barry Fussel. I'm a software engineer at Cisco Systems. Primarily work in common security modules or libraries. What I'd like to cover today is a little history on ACVP, some of the technologies that we want to target with this protocol, some deployment architectures, and then some of the specifics of the protocol. And obviously we're going to have a little demo at the end that shows exactly how it operates. Now, as a disclaimer, we are still in draft form, so we're still taking feedback from the working group. We're taking feedback from our internal people as well. So this is not a final protocol by any stretch of the imagination. A little bit of history. The ACVP was originally a David McGrew development from about 5 years ago, and there was actually a proof of concept performed then. Unfortunately, it didn't gain much traction within Cisco, so it stayed kind of stagnant. However, through the CMVP working group, has been revived, and we're using it along with their requirements, the lessons learned with the first proof of concept, and some other considerations that we've come up to help define what the protocol is going to look like. Well, first and foremost, it has to be automated. So one of the problems with the CABS implementation today for validation or algorithm testing is that there's a whole lot of files that are exchanged back and forth. So putting that in the protocol automates it. It also provides some level of scalability. Certainly we want it to be a remote validation so that this can be performed on-premise, hopefully one day at runtime, and we also will be using it for the service that NIST will be standing up. We have a phased delivery for features, including the initial thing is the algorithm test, basically the CABS algorithms that are supported today. In the future, we want to make that more intrusive so that we can get more information. And we use a version control so that we can, long term, we can use backward compatibility to test, again, deployments and hopefully runtime. So I think this has been brought up several times already as far as running software with vulnerabilities. And one of the considerations is we want to reduce that tension. We want to reduce that risk that's involved with running non-validated software. And clearly the validation through NIST and expediting the revalidations to speed up the FIPS validations is a primary focus as well. Some of the other targets, though, are within our development software lifecycle. We want to use this protocol to test as many points as possible during the lifecycle, from crypto module to integrating the crypto module into a product, and so on. And we'll talk more about that in a minute. And we want it to be as simple as possible. This will increase adoption, and it'll also be something, if the footprint is small enough, it's something that can be put in almost any product. So we were talking about the software development lifecycle just a minute ago, and I'd like to use an example that we have at Cisco, and that is that we have a crypto library that's used in many, many products throughout Cisco. That product is FIPS validated, and obviously at that point we could test it with ACVP for the FIPS validation. But then it gets integrated into the products, and we want to be assured that the integration team has done the right thing, has not broken something, has not touched something, so we can again test at that point. Pre-deployment and deployment are things that we feel like customers would benefit from, and for future runtime testing would be great. So in addition to the software lifecycle, the maintenance lifecycle. And again, I know we're beating a dead horse here, but there is this risk that people have to take if they want to continue running software that has vulnerabilities or running software that has not been validated yet. So our goal is to reduce that. How much we're going to be able to reduce that, we don't know for sure, but that's certainly top of the list as far as one of our goals. So let's talk a little bit about the protocol itself. What we wanted to do, and we wanted a lightweight standards track protocol built on top of existing standard protocols in encoding. We didn't want to reinvent the wheel. We wanted to use things that were already out there, TLS, HTTP. You see TLS as an optional protocol there. There's going to be environments, testing environments where TLS is not necessarily necessary. But for the most part, things where we're dealing with a validation authority, obviously it's going to be as secure as possible, and we want to use TLS 1.2 or greater. We chose JavaScript object notation, JSON, to encode all of the data. So the CAVS data that was used previously will now be encoded in JSON. Additional information will also be encoded in JSON, for instance, operating environment, exchanging capabilities, and that sort of thing. And we'll talk more about that later as well. We also wanted to provide some authorization using a JSON web token in order to help the server stay stateless. And again, similar to TLS 1.2 being optional, we don't define the authentication. The deployment is going to define the authentication used. So in a case like NIST, if they stand up a server, certainly they're going to use mutual authentication. We're going to have a client cert down at the test site. But if it's an internal test, as I was talking about before, if you're testing the integration purposes and that sort of thing, authentication may be not required. So let's talk a little bit about the deployment architecture. So this is the common NIST deployment for, say, a large organization. And on the left, you see the validation authority server. It's web hosted with REST API. It registers the proxy server. It will generate the JSON cat vectors. It will validate the JSON cat vectors, and it'll push the validation results to a trusted vendor ACV server. It'll also provide information to generate a cert for algorithm certs. The proxy server, again, this is sort of a large organization environment where we've got multiple devices constantly being validated. And this proxy server is going to front end all of those devices under test and perform the signatures that are necessary to send the results over. It's also going to do key management and cert management there, so that it doesn't have to be a part of the device under test. The proxy will forward the JSON test vectors down, take the responses, again, sign them, send them to the server. The client, in general, is going to be integrated into the device under test of the platform. Sometimes it could be a simulator. And it's going to convert the JSON test vectors if necessary. Hopefully, long term, the tests in the crypto module will understand JSON. But for today, most crypto modules understand CAVs, so we're having to convert those over today. And it's going to run it through the crypto module and return the cat vectors across to be forwarded to the NIST server. So we talked a little bit about other deployments, testing during the software lifecycle. And so this is a base architecture that would be used in that sort of environment. Again, we may not have as strong authentication. We may not have TLS for that matter. This could also be used in a smaller organization that doesn't need a proxy. And if that was the case, then we would be using authentication and TLS across the ACVP protocol. So let's talk about the actual protocol flows a little bit. Just maybe a show of hands, how many people are familiar with the CAVs format used? So a lot of you, and probably a lot of you have also filled out algorithm sheets or read algorithm sheets. Okay, so we wanted to leverage a lot of the good stuff that was there. I didn't want to reinvent the wheel there as well. And so some of that is incorporated into the flows that we use. So once the session is established, the client is going to post his operating environment and his algorithm capabilities. From there, the server is going to respond with a list of vector set IDs. Those vector set IDs basically represent a CAVS file, a single CAVS file. So what does that look like? So here's a register, and this is the registration portion of the message, and this is JSON encoded. Well, you have the vendor name, contact, module name, those sorts of things. Same exact stuff you'd see at the top of an algorithm sheet. You'd have the operational environment, the version of the module, processor, operating system, those sorts of things. So nothing really new there. We're just putting it into the messaging rather than having to fill out the forms. The second portion of this message is the capabilities exchange. Now, our demo and the slides are both just going to include AES GCM. And so the information here reflects the same kind of stuff that you see in the AES GCM information algorithm sheet. The server responds with a capability response and provides a list of vector sets. Again, those represent a CAVS file, a session ID, and an access token. This is the JSON web token, which basically gives authorization for the client back to the server. So the client, once he has the vector sets, will individually request a vector set from the server. So he's requesting one file. Since we're moving a lot of data, and so we want to just do these one at a time. So the server responds with the entire JSON encoded CABS information. So here's a partial example of that information. So again, we're dealing with AES GCM. Each test has its own ID. In this particular case, where our plain text is null and it provides a key in AAD. The client will run it through the crypto module and then post the response back to the server. The server will simply, if the message is formatted properly, will just respond with 200 OK. However, it has not at this point validated anything. It hasn't checked the results at all. And the reason for that is that many of these tests may take an extremely long time to actually run the results. So we're just getting a quick response back. The server can schedule a validation at some later time. So here's a partial response in JSON. The one thing that you'll notice here that is different between ACVP and CABS is that we only respond with the results. We don't echo all of the request information down. Once the results have been posted to the server, the client can monitor when, ask for the results to see if they passed or failed. It's my feeling, and it might not be everyone's feeling, but that probably won't be that much value there. I anticipate that most of the servers are going to have an out-of-band management website that you can monitor the results there as well. But if needed, the client can monitor to see when they are finished, and he'll get a result message back. There's a disposition that indicates the entire list of tests, whether they've all passed or incomplete or whatnot, and then individual tests will be identified as passed, failed, or incomplete. And now we can, what we're going to do, the demo is going to show basically the same flows that we just went through with some annotation, get you an idea of what's going on there, and it's going to show a lot of the log and JSON output, which would happen as a part of an AES GCM validation. Where'd you put it? There we go.
Nothing like a live demo.
All right, I think we have about 5 minutes for Q&A.
That's right. Please use the microphone. Thank you.
Are these mics on?
Not sure. Are these microphones working? Yes, they are. So if you gentlemen could answer questions on the microphone, we'll have an added bonus.
Perfect.
Can you get a little closer?
I had 2 questions about this.
Okay.
The first one is, how does the client know the appropriate and correct microphone on?
Go ahead and ask it.
Just be loud. Okay. Just be loud, no. Just be loud.
Just repeat it for the recording.
How does the client implementing this protocol know the correct and appropriate level of detail to report for things about operational environments? I saw you said Intel Woodward. How does it know to report that? How does it know that that's enough information?
Much like the algorithm sheets you have to fill out today, you have to fill out the exact same information. So a crypto module will initialize the client with, that information.
Okay, so someone's saying that in a config file somewhere?
Yeah, yeah.
Okay.
And that has to do with sort of the expectation of the program, what is the level of detail that the validation program would want for a specific environment. We'll go forth and back on the level of detail. In the past, we have talked about, for example, process families and try to obscure some of the details that preclude portability of modules, but the motivation for this protocol is different, so that if you need slightly different environment, because it is so automated, you could just test that and not worry about what level of details that you may want to specify on your environment. That's essentially a small deviation from the legacy approach to defining the details of the operational environment.
Thank you. My second question was, was about what happens if it shows a fail, because you showed the past example responses.
Sure.
Have you defined a fail state, and does it provide enough information to allow them to debug what went wrong the first time?
Absolutely, and that's one goal I did not mention. The intent is to provide a lot more triage information within the protocol. So in general, if the client fails, it fails. All right. So, but it is going to be reported there, and the disposition would be a failure, and then the information exchanged or sent back on the failure should indicate some more details than we get today. I mean, today we get almost nothing, right? So hopefully we're able to generate. It could be a JSON formatting issue that caused the failure.
Right.
It could, we would want to point out exactly which test ID failed and things of that nature. That if the AAD was right, or the ciphertext was right, but some other piece was wrong, we would want to indicate that. So hopefully we'll be able to provide some details there.
Okay.
We have time for one more question.
So how is this going to relate to overall FIPS testing? Because this is just one piece of FIPS validating a module, right? We're not getting into the actual module testing. So is the intent here that you go through the normal process, or whatever the process is today, maybe some modification in the future, and then once that's done for a certain time period, you can do this before we have to revalidate the entire thing? How is that going to work?
All right. Well, as I said, this is just one of the work area, and it's the first milestone. We're happy to report it's the beginning of a long road. And so, yes, we want to cover as much as possible with the automation. And so it is mostly a question for the industry to help us understand what's automatable or not. And based on the outcome of this conversation, we'll decide what the next milestones are and put some time frame around them. But this is definitely not the end of the road, I think.
Great. Well, thank you. Really fast, Chris. Yeah. Super fast.
Just a quick comment. I think that assuming that you want to automate the validation process, say a module goes through validation and it passes. However, there's some kind of patch that needs to go onto the device. Maybe by running this tool against the, or running a separate set of test vectors with the module that has been patched, you can verify that the algorithms still work correctly. And maybe you can still, keep the validation current by having those algorithms revalidated, if you want to call it, based on the patch management that's occurred as part of, fixing bugs, assuming that you're not adding features. That's a consideration you might want to add to your.
We're considering, if you recall, last year we tossed out this idea of the 3-tier system and trusted vendors, and some of the thinking there was around the same sort of ideas. If you have done multiple module validations and you're just fixing a couple of things here, maybe you can get a pass with just doing algorithms. So these are open questions for the working group to sort of discuss and agree on.
Thank you very much, Fussel and Barry.
Yeah.
All right. Dee, come on up the stairs right here.
Oh, okay, no problem. Thank you.